All right, well, good afternoon, everybody. Looks like it's 1 o'clock, so we'll go ahead and get started. And I'm recording the session, so go ahead and get going. So, what I intend to do today is to go over what you would have done in lab, but we're just going to make it a virtual lab. I'm just going to basically take you through the pre-lab assignment and the post-lab assignment, explaining the experiment that would have been done and then really just give you the keys and the tools that you need to answer the questions in those two assignments. And we'll just call that the grade that you get for this lab. So we're not actually going to, have to make up a lab that may or may not be missed because as I think I mentioned in class, I don't think that we will even meet for class on Thursday. We'll see. If it's not up to me, of course, but even if campus is officially open on Wednesday or Thursday, we will not meet for lab. There's no need to do that. Well, this video, in a sense, is the lab. Okay. All right. So without further ado, because I know I've got a time limit on these Zoom meetings, I'm going to go ahead and go to lab assignments. Oh, by the way, though, so if you do have a question, if you need to interrupt me, uh, that's fine, but just go ahead and either type it in the chat box. I'll be looking at the chat box, or feel free if you need to just take yourself off mute and interrupt me. If I say something wrong or confusing, I want to correct myself as soon as possible. All right, here we go. So going back to the Blackboard site for this course, if you go to lab assignments, we'll talk through both the pre-lab assignment and the post-lab assignment. Okay, so the Lab 5 pre-lab assignment, let's talk about it. All right. So, what I would do actually is for now, I wouldn't try and follow along in the assignment. I would just maybe take some notes if you've got a piece of paper handy, take some notes, uh, and then just go back and do this assignment later. All right. So, in the pre-lab assignment, the first question asks, what's the molar mass of a compound that we would be working with in this experiment? Copper 2 sulfate pentahydrate. All right. So I'm confident you know how to come up with the molar mass for that. Remember, you would just use the periodic table. You would find the average atomic mass for each of these elements, atom types that are in this compound, and then just multiply times the number of atoms that are there. Like you'd multiply the average atomic mass of oxygen times 4. You'd multiply the average atomic mass of hydrogen times 10, because there's 5 waters and each water has 2 hydrogens in it. Okay, but to cut to the chase, um, if you don't mind, I'll just go ahead and punch in the number here. So the number would be 249.7 when you round to 4 sig figs as directed. To 249.7, okay, is the molar mass of copper sulfate pentahydrate. Now, of course, the reason why we want that molar mass is because we're going to use it in a calculation, which comes up in question number 2. All right, so it says calculate the number of moles in 3.58 grams of copper sulfate pentahydrate. And by the way, you probably will not get in your assignment exactly, 3.58 grams. It will probably generate a different number for you when you do this calculation. All right, but here's how we would do it. So we have 3.58 grams of copper sulfate pentahydrate. Okay, and I just determined in the previous question that 1 mole of copper sulfate pentahydrate is 249.7 grams of copper sulfate pentahydrate. Okay, so grams over grams cancel, and I have units of moles, which is what I'm looking for. Okay, so I just need to punch all that into my calculator to get a number of moles of copper sulfate pentahydrate. Okay, so if I do that, basically I'm going to be dividing 3.58 by 249.7, and I get, and I want 3 sig figs, so that would be 0.0143. So we go back to this, 0.0143. Okay. All right. So hopefully you remember how to do that. That's a skill set we already hopefully developed back in Unit 2, converting grams to moles. Okay. So then the next question, let's see if this goes away. I got to clear away all the drawings here. Okay, so then the next question really just has you watch a video, and we're not going to watch the video right now, but you should watch this video when you do this assignment. And the reason why is because it talks you through a new type of reaction called a single displacement reaction. And that short little video will introduce you to that type of reaction. But comparing it to what you already know about, the double displacement reaction, the gist of it is that you have a single displacement, okay? And that's because, let's say I have compound A, or pardon me, pure element A reacting with a compound that's just B and C, okay? The product is going to be A is going to displace B, right? And so B is just going to become the pure element, and then the A that was part a pure element is going to become part of the compound. So that's what we mean by a single displacement. One thing gets displaced. In this case, the B gets displaced, gets replaced by an A, and then whatever got displaced or replaced becomes a pure element. Right? That's the characteristic thing of a single displacement reaction, because that's what's going on in this experiment. In this experiment, you have aluminum wire reacting with a copper compound that's in solution, and the aluminum becomes a compound which goes into the solution, and then the copper becomes a pure metal and it plates out on the piece of aluminum wire. And you'll see that when we bring up the post-lab assignment. Okay, but one thing about single displacement reactions is it doesn't happen. I'm going to leave it up there actually to talk about this next question. So it doesn't happen all the time. And what dictates when it will happen and when it doesn't happen is this thing we call an activity series. All right. So that is something that's also introduced in that video that I referred to earlier that I'll let you watch on your own. Okay. So as I mentioned, in the lab, what you do is you react this copper sulfate with an aluminum wire. So that would be like aluminum solid. Okay. And then what happens is it displaces the copper in the compound, and you would get aluminum sulfate. Okay, but here's the thing is that it's not going to be the same compound because aluminum likes to be a +3 ion because of its position in the periodic table, remember. Whereas copper, this is a copper +2. That's why it's one copper +2, and the sulfate you memorize SO4 is 2 minus. So that's why it's 1 to 1. One copper for every sulfate. But with aluminum, because it likes to be a +3, you're going to have 3 sulfate. So that needs to be a subscript 3. And then remember, as we said before, the sulfate has a, like a charge of -2. So that would become a subscript on the aluminum. So the compound formula would actually be Al sub 2 parentheses SO4 sub 3. Okay. So to keep things balanced, that means I need 3 sulfates over here, and I need 2 aluminums over here. So let's do the sulfate first. So the 3 sulfates puts a coefficient of 3 right there. Okay. And then I put a subscript of 2 on that aluminum. So that puts a coefficient of 2 there to keep things balanced. And so now this 3 also needs to come over here to give me 3 copper. So I'll make it a coefficient of 3 to balance the coppers. Okay, so that's a little bit messy, but hopefully you see what's going on. I just had to balance that reaction. But this would be the single displacement that's occurring in the experiment that you're doing. Okay, now here's the reason why. We get into this a lot more in Chem 2. We really just introduce it in Chem 1, but if you have to take Chem 2, you'll see this happens. You get a lot better explanation for why all this happens. But here's the thing with an activity series. The reason why I know that aluminum would do this, why aluminum would displace the copper, is because aluminum in this activity series is above copper. So everything above copper, which is hydrogen, lead, tin, iron, zinc, carbon, aluminum, there it is, aluminum. Okay. So this is the reason why I knew that this reaction would occur, because aluminum is above copper in the activity series. Okay, so that will help us answer this question. Which one of these metals would, like aluminum, react with copper sulfate and do a single displacement reaction? Well, we already decided the aluminum would because it is above copper in the activity series. Well, what else in this list should I choose? What else is above copper in this activity series? Okay, well, I won't spoil it for you. I'll let you figure that out, but hopefully you understand how you'll get the answer. You're just going to look in this list for the elemental symbol that is above copper in the list. So I'll again let you do that on your own. Okay? All right, so I think that's pretty much it for that assignment. Yeah, that's it for that assignment. So hopefully now you feel like you got the necessary skills you need to do well on this assignment. All right. And I just want to check and make sure I didn't lead you astray on those first two. Yeah, I got the right answers on those. These are counted as wrong because I just didn't really submit answers, but particularly the one that I actually did the calculation on, I did it right. Just wanted to make sure. Okay. Okay. So now I want to go ahead and talk you through the post lab assignment. Now you notice that you guys should not be able to see the post lab assignment yet. And that's because there's one question that I'm going to add to this. And that is, hey, did you either participate in this live session, or for the people who can't and watch the video later, they can document that they participated by watching the video, and you'll get some credit for that. But and again, what I recommend is that you just listen, observe, and take some notes that will help you when you go back to do this assignment later. Okay. So I'm going to just walk through this assignment here. So in this first question, it just shows you what's going on in this experiment. We already balanced the equation, okay? And here's what happens. You were going to put a piece of aluminum wire. You're going to put a piece of aluminum wire in a test tube with a solution of copper sulfate. So copper sulfate, when it's in solution, it makes a blue solution. That's why it looks kind of blue. All right. And the aluminum solid is this coiled up wire that you see in there. Now, the wire that we were going to put in the solution wasn't going to be coiled up. It was just going to be like a stick. Okay. And then you give it time. And what happens is all of the, as the displacement takes place, the blue disappears and becomes colorless. And that's because the copper ions are what is responsible for the blue color. So if the copper ions come out, then it loses the blue color. And what you'll see then is that the surface of that aluminum, because the aluminum is reacting and going into solution to form this aluminum sulfate compound that's aqueous, okay, and the copper is coming out and forming copper solid. Well, we know that copper is kind of a reddish brown color, and that's what we see here. This is a very, nice illustration of the copper ions that were in the solution have plated out as copper metal, that brownish red metal, on the surface of that aluminum. And that's what you see here. Okay? Okay. So we know the balanced reaction. We observe what actually happens. The color in the solution goes away. It goes from blue to colorless. The surface of the metal becomes, instead of a shiny silvery kind of color, it becomes this, rugged looking red brownish kind of wire. That's because the copper that was in solution has plated out and formed those, crystals of copper metal on the surface of that aluminum wire. Okay. So, but how do we do the calculation? So we're given a mass here of 0.786 grams of copper sulfate pentahydrate. It's dissolved in this solution. All right. So if it completely reacted, if every one of those copper ions plated out as copper metal, what would be the theoretical yield of the copper? So if I were able to scrape off all of that copper, how much copper would it be theoretically? All right, so this is basically a stoichiometry calculation. So let's talk about how to do that calculation. Okay, so again, you're always going to start with the number that you're given that's not going to be used as a conversion factor. Well, in this case, that's not hard to choose because I'm only given one number, and that's the 0.786 grams of copper sulfate pentahydrate. So let's start there. Okay, so we got points 786. No technical difficulty, please. 0.786. Start over. 0.78. I'm sorry. This is just not cooperating with me today. Why is it not cooperating with me today? Maybe if I make it a little thicker. Try that. Okay, copper sulfate pentahydrate. All right, so we said that we need to change that into moles. Nothing happens in chemistry on a gram basis, it happens on a mole basis. So 1 mole of copper sulfate pentahydrate is 249.7 grams of copper sulfate pentahydrate. All right, so that has grams over grams. So now I'm in moles of copper sulfate pentahydrate. So what I need to do is I need to convert from moles of this into moles of copper metal, because that's what I'm after. Theoretically, how much copper will get plated out? Well, you can think of it as either a 3-to-3 ratio or 1-to-1, whatever makes the most sense to you. I've taught you before that you can just use the coefficients in your balanced chemical reaction. So that's the way that I'm going to represent it in this calculation. So 3 on the bottom, 3 moles of copper sulfate pentahydrate. Sorry about that. My voice is still not fully recovered, and I've still got a little bit of a cough. Will produce 3 moles of copper metal, CuS. Okay, 3 and 3. All right, so now my units of moles of copper sulfate pentahydrate cancel, and I have units of moles of copper metal. But what I want is the theoretical yield in grams. That's what we're asked to find. So I need to go one more step, and I need to convert that into grams of copper. Okay, so 1 mole of copper solid is, you know what? Let me look this up real quick. I know approximately what it is, but I want to make sure I don't write the incorrect number down. So on my phone, I'm just going to Google it. 63.546 grams. Okay. 63.546 grams of copper solid. Okay, again, my chicken scratch is really not good today. 63.546 grams of copper solid. Okay, so that gives us the units that we're looking for. Everything canceled except for grams of copper solid, and that's what we're after. So once again, this is another one of those questions where you're probably not going to get 0.786. So, you don't want to just write down the answer and then put it in later. You want to write down, the solution, the actual calculation, because you will probably be given a number that's different than 0.786. All right, but here we go. So 0.786 times 3 times 63.546, enter, divided by 249.7, enter, and then divided by 3, and you get 0.200. So I'm getting your time's almost up, alert. Okay, that's okay. So what you get is 0.2. Okay, so 0.2, 0.200. All right, so that would be 0.200. Okay, so that's how you would calculate theoretically how much copper got plated out. All right, so let me clear all these drawings away. And now let's talk about the other question here in this assignment with the time that I've left. Oh, yeah. Yeah, I won't have time, but let's talk about how to do this actual yield and percent yield. And I'll not be able to get into oxidation numbers. Maybe I will. Let's see, I've got 11 minutes left. Let's try. I'm going to try. Okay, so let's say that we've got this data here where I want to figure out the percent yield. Okay, so the actual yield is going to be different than the theoretical yield. And to sort of characterize how good the experiment went, we have this parameter called the percent yield, where the percent yield, we've done a calculation like this before, where the percent yield is just equal to the actual divided by the theoretical, okay? And then we multiply times 100%. Okay, so in this case, the actual yield, um, so So we want to use the formula to calculate the percent yield if 0.092, so that's the actual. So if 0.092, so 0.092 grams, and the theoretical yield, now, it's not the same calculation we did before. So let's say that it was 0.241 grams, and then times 100%. Okay, so I won't finish that calculation so that you can just do it on your own. And again, you may be given slightly different numbers for both the actual yield and the theoretical yield. Be on the lookout for that. Okay, it may not be these exact numbers, but the technique is going to be the same. Okay, all right, clear that away. All right, so as I said before, you're going to watch a video that will explain something called oxidation numbers. Now, oxidation numbers, they're similar to electronegativity, which is a property that we're going to learn about later in the course, but it's a little different. And we're just introducing it in Chem 1. You go into this a lot more in Chem 2. Okay, but let me talk you through it real quick. So oxidation number talks about or characterizes that within a compound, does an atom relatively take on positive character or negative character or neutral character? So it's just somewhat of an arbitrary way to characterize atoms in compounds as either positive, negative, or um, neutral. But there are some rules that you got to follow. So let me explain very quickly what those rules are, and then we'll go through at least one example here. So, if we have a compound, let's say, well, let's just use it here. No, actually, let me lay out the rules first. So we'll just say like a rule, and then the oxidation number would be something. So, in a pure element, any kind of pure element, it's easy. The oxidation number is always zero. Okay. Any for an ion, the oxidation number will be the same as the charge on the ion. Okay. Then there's some elements that have reliable oxidation numbers. You just know that they're going to have a certain oxidation number. So oxygen, and it's not a zero, it's oxygen in compounds. I'll abbreviate compounds. Its oxidation number is reliably a -2, something you can hang your hat on. If oxygen is part of a compound, its oxidation number is going to be -2. Hydrogen in compounds is going to reliably have an oxidation number of +1. And then fluorine in compounds is going to have an oxidation number of -1. Okay. And then everything else you just have to calculate. And what you do is you find some starting point, which is most likely going to be one of these three elements, and then you kind of work from there to figure out the oxidation number of the other atoms. Okay, so what I'll do is I'll try and walk you through these three questions, and I'll let you do three of them on your own. So, for example, what is the oxidation number of aluminum in aluminum solid? Right there. What's the oxidation number of that? Well, what is it? That's a pure element. That's solid aluminum, which is a pure element. So I know that its oxidation number is zero because the oxidation number for pure elements is always zero. Okay. Well, what's the oxidation number of copper in copper sulfate? Well, you got to remember that it's not really copper sulfate. What that is that's copper ions just coming together with sulfate polyatomic ions. The compound is just those two ions that are attracted to each other. They're working together because of electrostatic forces. That positive charge is attracted to that negative charge. So what we really have here is we have a copper 2 plus ion. And as we said in our rules, our list of rules here, that the oxidation number for an ion is the charge on the ion. So the oxidation number on copper in this compound is just the charge on the ion. So it's either 2 plus, or you could do +2. It really is just kind of by convention, it's that they mean the same thing. So I think in this box you can type in 2 plus or +2. Okay. All right, so what about this next one here? Um, no, actually, you know what? I'm not going to do this one. I'm going to let you answer this one right here. I'm going to skip down. I'm going to answer this one. What is the oxidation number of sulfur in SO4 2 minus? Okay, so sulfur in SO4 2 minus. Okay, so here we go. So I got 5 minutes left. I got enough time. So in SO4 2 minus, I said earlier in my list of rules here that oxygen is reliably a minus 2. Well, there are four oxygens in sulfate. It's SO4. So that's 4 times minus 2. So the oxygens are bringing into the mix a total of minus 8. Right? There's four oxygens. Each of them is going to be minus 2 because oxygen, when it's part of a compound, is reliably minus 2. Right? So that's a total of minus 8. But overall, I got to notice that my charge on this ion is just minus 2. Okay? So that must mean that the sulfur is counteracting 6 of these minus 8s. Okay? So it's like there's 8 negative charges. 1, 2, 3, 4, 5, 6, 7, 8. There's 6 of those negative charges in this polyatomic ion, and the sulfur must be canceling out 6 of them. Leaving 2 left. That's why overall the sulfate, the SO4, has a charge of minus 2. So that means that the sulfur must be plus 6. Okay, that should be a plus sign. So that's my answer. So what is the oxidation number of sulfur in SO4? It's got to be a plus 6 because, again, each of those oxygens is minus 2. And overall, the ion has a charge of 2 minus. So 4 times 2 is minus 8. Overall, I got to keep 2 of those minuses. So the sulfur must be canceling out 6 of them. So that means the sulfur has got an oxidation number of plus 6. Okay, so that should be enough, I think, to help you along with the video to answer the rest of these questions. And of course, you can come see me or email me if you need extra help. Okay. All right, so I do have a couple minutes left, so that's pretty much it. If you just do that and you submit it, once I open this assignment up for you, you should be able to submit it, and then you're good to go for this experiment. We won't actually do the experiment. So we do have a couple minutes left on the clock. If you want to ask any questions, I'll go ahead and shut up. And like I said, you can either take yourself off mute. If you want to log off, you can, or if you want to just type it into the chat box, you can do that too. All right. I know that was probably incredibly boring for most people sitting in, and I do understand. So, if there are no takers, and it looks like there's not, I'll just go ahead and close things up and stop there. So, everybody, stay safe, stay warm, and just stay tuned also for what's going to happen tomorrow. I don't know. I'll send out an announcement. All right. Thanks.